Assalamualaikum and good morning everyone. Today, we will present our molecular dynamics simulation using Lammps and Ovito. In this work, we simulated argon and copper atoms and studied how temperature affects their atomic behavior. Lammps was used to perform the molecular dynamics simulation by calculating the forces and movement of atoms. Ovito was then used to visualize the simulation results in 3 dimensions. For this project, argon was simulated using the Lennard-Jones potential, while copper was simulated using the embedded atom method or EAM potential. We also changed the temperature to observe its effect on atomic vibration and structure. For argon, the Lennard-Jones potential describes the attractive and repulsive interactions between atoms. The potential energy surface helps determine the equilibrium distance between atoms. The Maxwell-Boltzmann distribution explains how atomic velocity changes with temperature. For copper, the EAM potential is more suitable because copper is a metallic material. It considers both pair interactions and the surrounding electron density. During the simulation, Newton's equation of motion are solved at every time step to update the atomic positions and velocities. Before running the simulations, we first downloaded and installed Lammps and Ovito Basic. For Lammps, we visited the official Lammps website and downloaded the latest 64-bit Windows installer. After downloading, we ran the installer and completed the installation using the default settings. Once installed, Lammps provide the LMP-exe executable, which is used to run our input scripts through the command prompt. Next, we downloaded Ovito Basic from the official Ovito website. We selected the Windows version, installed the software, and used it to open the trajectory files generated by Lammps. After both software packages were successfully installed, we prepared our input scripts, ran the molecular dynamics simulation in Lammps, and finally visualized and analyzed the atomic structures using Ovito. First, I will explain the argon simulation. After installing Lammps, we created an input script called argon.in. Inside the script, we first selected Lennard-Jones units because argon is a noble gas. Then we defined an FCC crystal structure, created the simulation box, and generated the argon atoms. Next, we selected the Lennard-Jones potential by using the pair_style lg/cut and pair_qf commands to define the interactions between argon atoms. After that, we assigned the initial atomic velocities using the velocity command with a reduced temperature of 1. We then applied the NVT ensemble using the fixed NVT command to keep the number of atoms, volume, and temperature constant throughout the simulation. The simulation was run for 10,000 time steps using the run 10,000 command. To execute the simulation, we saved the input file as argon.in, opened command prompt, navigated to the folder containing the input file, and entered the command lmp.exe-in-argon.in. Once the simulation finished, Lammps generated the output files including the trajectory file argon.lamp.strj and the log file log.lamps. Finally, we opened the trajectory file in Ovito to visualize the atomic structure and observe how argon atoms vibrated during the simulation. These images show the original argon simulation at a reduced temperature of 1. The atoms stay arranged in the FCC structure. During the animation, the atoms vibrate around their equilibrium positions. The structure remains stable because the temperature is controlled using NVT ensemble. For the parameter study, we changed only one parameter, which was temperature. The reduced temperature was increased from 1 to 2. The velocity command was changed to create higher initial atomic velocities, and the NVT temperature setting was also changed to 2. Temperature was selected because it directly affects the kinetic energy of atoms. A higher temperature means the atoms move and vibrate more strongly. These images show the argon structure after the temperature was increased to 2. The atoms still maintain the overall FCC arrangement, but the vibration becomes stronger. This is caused by the increase in kinetic energy. From the comparison, at temperature 1, the atoms vibrate with lower kinetic energy. After increasing the temperature to 2, the atoms vibrate more vigorously. However, the FCC structure is still maintained within this simulation condition.
Next, I will explain the copper simulation. After completing the argon simulation, we perform a molecular dynamic simulation for copper. First, we created an input script called copper.int. Since copper is a metal, we selected units metal, which uses angstrom for distance, picoseconds for time, electron volt for energy, and Kelvin for temperature. Next, we define the FCC crystal structure of copper using a lattice constant of 3.615 angstrom. Then, we created the simulation box and generated the copper atoms. To accurately describe the interactions between copper atoms, we used the embedded atom method EAM potential. This was done by specifying pair_style EAM and pair_COEFF CU_U3.EAM. The EAM potential is suitable for metals because it considers both the interaction between atoms and the surrounding electron density. After defining the atomic interactions, we assign the initial atomic velocities using the velocity command at 300 Kelvin. We then apply the NVT assemble using the fixed NVT command to maintain a constant temperature throughout the simulation. The simulation was performed for 10,000 steps using the run 10,000 command. To execute the simulation, we save the input script as copper.int, place it together with the CU_U3.EAM potential file in the same folder. Open command prompt, navigate it to folder, and enter the following command lmp.exe in copper.int. After the simulation finished, Lammps generated the output files, including the trajectory file copper.lammps.trj and the log file log.lamps. Finally, we open the trajectory file in Ovito to visualize the atomic arrangement and observe how the copper atoms vibrated during the simulation. These images show the original copper simulation at 300 Kelvin. The atoms are arranged in a regular FCC crystal structure. During the simulation, the atoms vibrate slightly around their equilibrium lattice positions, but the overall crystal remains stable. For the copper parameter study, the temperature was increased from 300 Kelvin to 600 Kelvin. Two lines are modified. First, the velocity command was changed from 300 to 600 Kelvin. Second, the NVT temperature setting was also changed to 600 Kelvin. The purpose was to study how higher thermal energy affects atomic vibration in the copper crystal. These images show the copper simulation after increasing the temperature to 600 Kelvin. Compared to 300 Kelvin, the atoms show larger displacement and stronger vibrations. However, the atoms still maintain the FCC crystal structure because the 600 Kelvin is still below the melting temperature of copper. At 300 Kelvin, the copper atoms oscillate slightly around their equilibrium positions. At 600 Kelvin, the atoms have higher kinetic energy, so their vibrations become stronger. Even though the atomic movement increases, the FCC structure remains stable.
Overall, argon and copper both use FCC structures, but they use different interaction potentials. Argon uses the Lennard-Jones potential because it is a noble gas with simple atomic interactions. Copper uses the EAM potential because metallic bonding depends on the surrounding electron density. For both materials, increasing temperature causes stronger atomic vibration due to the increase in kinetic energy. In conclusion, we successfully completed the molecular dynamic simulation of both argon and copper using Lammps, and we successfully visualized and analyzed the simulation results using Ovito. From the simulation results, we observe that the increasing the temperature increased the kinetic energy of the atoms. As a result, both argon and copper atoms showed stronger atomic vibrations and larger atomic displacements. This project also allowed us to gain practical experience in preparing Lammps input scripts, selecting suitable interatomic potentials, running molecular dynamic simulations, and analyzing atomic behavior using Ovito. Through this activity, we developed a better understanding of how simulation tools can be used to predict and study material behavior without performing physical experiments. That is all from us. Thank you for your attention. We hope our video has provided a clear understanding of how Lammps and Ovito can be used to stimulate and analyze atomic behavior.